We're going to start the new semester and the new quarter by talking about physics, and the remainder of the year will be physics. And we'll start out by talking about simple things like energy. Now, energy is defined as the ability to do work. And the SI, or Systems International Unit for Energy, is called the joule. And a joule represents a kilogram meter squared per second squared. So it's in kilograms and meters. So when we calculate things in kilograms and meters, we end up with joules. Another unit for energy is an erg, E-R-G, and that's when you use grams and centimeters instead of kilograms and meters. Now, this process that we're going to be going through initially is the study of mechanics. And the study of mechanics is the study of motion and forces. And the diagram here simply shows the effect of various positions in space on kinetic and potential energy, Ke and Pe, two things we'll be talking about at length here in just a minute. So at the bottom of a hill, when a cart is moving, it's maximal kinetic energy and no potential energy. When it stops at the top of the hill, its kinetic energy has gone to zero, but it has a great deal of potential energy by virtue of its position. When it goes down the other side on the right, in the middle of the hill, it still has some potential energy left, but some of that potential energy has been converted into kinetic energy by its motion. So what are some various forms of energy that we'll be taking a look at over the next several weeks? Well, I just mentioned kinetic energy. Kinetic energy is the energy of motion, or the energy that a body has because it is moving. And a body that has no motion has no kinetic energy. Now, we will not be talking about the motion that's caused by the movement of the earth and this sort of thing. We're going to talk about the earth being the frame of reference, so that it's motion relative to a earth that appears to be not moving. Potential energy, on the other hand, is energy that a body has because of the forces that are acting on that body. Now, one such force is gravity. And when gravity is that force, sometimes this is called the energy of position. And in order to define potential energy, you always have to be able to define the ground level. And then how much above the ground level you are is how much gravity is causing the potential energy that the body has. The third type of energy, which we'll talk about later in the year, is radiant energy. Now, we'll actually talk about it a little bit in this today in one of these segments when we talk about radiant heat. But generally, it's the energy of electromagnetic radiation. And one of those electromagnetic radiations that we'll ultimately be talking about is light. So here's another way of looking at the various forms, and some that I didn't mention that are on this diagram. If you look at the bottom, for example, you can see that there's chemical energy and electrical energy. You can see on the left there's nuclear energy, and the ones that I have mentioned are mechanical, thermal, and radiant energy. And we'll come back and talk more detail about mechanical and radiant energy. Now, there are certain laws that energy follows, just like anything else, and one such law is the law of conservation. And what this law says is that energy cannot be created or destroyed, but only changes form. Now, this law has been in effect since people have been writing laws in physics. And what this says is that when energy is transferred from one object to another, generally the properties of matter will change within that object. Now, since Einstein, it's been found that matter can be converted into energy. Now, this is a new concept. This was not something that was believed before Einstein came along. And as it turns out, he made the calculation stating that the energy that would result if matter was converted into energy is equal to the mass of that matter times the speed of light squared. Now, because of this new idea that matter can be converted into energy, we have to revise our law of conservation and say that we are now talking about the law of conservation of energy and matter, or matter and energy. And so if matter is lost, obviously energy would increase, but then there's a conservation if you take both the matter and the energy into account. But for the purposes of this class, I would focus on the idea that energy cannot be created or destroyed. So, energy cannot be created or destroyed. However, energy can change form. But because it cannot be created or destroyed, the total amount of energy has to remain the same. So, we were talking about kinetic energy, and one type of kinetic energy is called whole body kinetic energy. And whole body kinetic energy is the energy of an object by virtue of its movement from one point to another. Sometimes this is also called translational kinetic energy because you're moving or translating a body from one position in a linear fashion to another position. So this type of kinetic energy, the formula for this, Ke, is equal to 1/2 mv squared, where mass is m and v is velocity. Now, since we're working in joules, the mass needs to be in kilograms, and the velocity needs to be in meters per second. So let's look at a couple of problems related to this type of situation. This first one states that a runner that we just saw in the previous slide is running, and he has a mass of 70.0 kilograms, and he has a velocity of 2.85 meters per second squared. So what kinetic energy, or what translational kinetic energy, would he have? So the kinetic energy, translational kinetic energy, is going to equal to 1/2 times his mass, which is 70.0 kilograms, times his velocity, which was 2.85 meters per second, and that value would be squared. Now, I don't have a calculator on me, so you can do the mathematics here, but if you do this calculation, you'll find what kinetic energy he has. Well, let's look at this second problem. A rock is dropped from a ledge and it hits the ground with a velocity of 20 meters per second. If the rock in that process imparted 3.8 times 10 to the fourth joules of energy, what would that rock's mass be? Well, how would we do that? Well, we know that Ke is equal to 1/2 mv squared, and we're wanting to solve this equation for mass. And so we multiply by 2, so 2 times Ke is going to equal mv squared. And so the mass is going to equal 2 times the kinetic energy divided by the velocity squared. So if we put that in over here, it would be 2 times 3.8 times 10 to the fourth divided by 20 squared, or 7.6 times 10 to the fourth divided by 4 times 10 to the 2. And I can actually do this one in my head. It would be 1.9 times 10 to the 2, or 190 kilograms. So that would be the mass of this object based on these calculations. Now, it's important to understand that that's not the only kind of kinetic energy that exists. And there's something called rotational kinetic energy. Rotational kinetic energy is an energy that an object has by virtue of its movement along its central axis. And in order to understand this, you really have to differentiate between rotational motion, which is on the left, where this is the central axis, and this body is moving around this central axis. So this is rotation. And circular motion, in which the body moves and has a center of radius of its motion, but it is not necessarily rotating. And when we talk about rotational energy, we're talking about the one on the left, not the one on the right. The one on the right is, we talk about some in another way. And so in order to calculate this, we have to see that this energy occurs as you rotate around this central axis, and there are formulas for doing that calculation. Now, potential energy, on the other hand, is, as I said before, it's by virtue of the fact of forces acting on an object. And the forces can be different forces. Now, over here is gravitational potential energy. This is the potential energy that occurs on an object because gravity is acting on it. And it is energy that can be released if this car were to go either way down this mountain. Now, so this type of potential energy, which has also been called translational potential energy, is equal to the mass times gravity, because that's the force that's acting on it, times the height. And the height is defined by saying that this bottom of this hill is 0, and however far above that is the potential energy in this system. So mass, again, has to be in kilograms, and height has to be in meters. Now this side we won't be talking about at length, but this is another type of potential energy called elastic potential energy. And that is by virtue of the force of this spring, in this case, acting on this ball when it's moved outside its resting position. And that's equal to the constant of the ball, which corresponds to G here, times 1/2 times the distance it's moved from its resting state squared. And this is called elastic potential energy. So let's look at a couple problems, again, with the potential energy in mind. A rock has a mass of 71.6 kilograms and is placed at a height of 32.4 meters. If gravity is 9.8 meters per second squared, what is the potential energy? Well, this is how we would calculate this. We remember that PE is equal to mgh, which is equal to, in this case, 71.6 times G, which is 9.8, times H, which is 32.4. And again, I don't have a calculator, but you can do the math here, but the answer that you get is going to be in joules. Now, it talks about this rock, again, if it has a potential energy of this much, how high off the ground or how high above the baseline would it have to be? If we take this formula and solve for height, then we would have PE divided by mg is equal to h. And so the PE here is 3.123 times 10 to the 5th, and M is the same. It's going to be 71.6, and G is going to be the same, 9.8. And so if you do this math, you'll find how high it would have to be in meters in order for this to have this much potential energy. At this point, I'm going to stop the tape, and we'll go to another segment to talk about thermal energy.